No, absolutely not.
Yeah, is that okay? Okay, so we'll start. Okay, cool. Well, good morning. I think one of the things is that as a Microsoft research person, I don't get a host, so I just have to introduce myself. My name is Derek McAuley. I'm from the Cambridge lab. I was one of the three of us who founded the lab there just over 3 years ago. Myself, Roger Needham, who's the boss, and Chuck Thacker, who has since moved on to things like ebooks. So today I thought I'd just take a few minutes to run through some of our activities. I haven't been exhaustive on what we're up to at Cambridge. Those of you who are in the relevant fields, who, say, I think of the Andrew Blake's here from our vision group, I'll be talking about some of his work and other researchers' work, and of course if they're in your field you may well know quite a lot about it already, but this talk's a general overview just to give you a general idea of the research areas we engage in at Cambridge. And it's a bit of a mishmash of subjects, and the information you're going to get is basically from those people who are self-publicists, because I send out email and said, what do you think that's neat that you've done recently that I can present? And so if it's not present, it's because people didn't come to me and say, hey, I think this is really neat. But without further ado, so we started this lab in '97, and the goal was originally to grow to about 40 researchers. And although we weren't told it at the time, that seemed to be the sort of number that would be a good number to be a critical mass, especially given that we're associated with the university. And we have lots of collaboration with the university. That gives us, an intellectual critical mass to be a research lab. However, within about 18 months, Rick decided we seemed to be doing a good job, and so we've continued to grow from that number 40. We are a European lab, not just a British lab. I mean, it's obvious that there are more than our... there's a stronger presence of British in the lab than there is other nationalities, but the alias MSRC Frog, which is for discussions of French matters, has 11 members on it. I should point out that it was a Frenchman who actually came up with the name. And we currently have 12 nationalities from across Europe. We are now up to about 50 researchers, and then together with some administrative staff and IT support locally, and also university relations, or I should say that part of university relations that is concerned with research, so it's sort of a small piece of what Doug Leyland does here. We have 65 full-time people altogether. One of the things that we have observed is lots of people like to come to Cambridge. I'm not sure whether they like to come to visit us or whether they like to come to visit the university, but they like to come to Cambridge. And at any time we have, basically I allow for up to 50% on top of our full-time staff for people visiting, people wanting to come on sabbaticals. And I think they want to come to Cambridge, and they like to come to us because we'll pay them as well. So there is a pretty close collaboration with the university. Originally it was, our view was that it would be working closely with the computer laboratory. And that's true in those subjects such as computer languages and theory and security and systems. We do work with the computer laboratory. But since we have expanded our areas of research from starting out, in fact, we work closely with engineering because for historical reasons, vision and speech recognition is actually in the engineering department in Cambridge rather than in computing. And indeed, on the networking side, we have some work at the fairly theoretical end of teletraffic and modeling networks. And that work actually carries on in collaboration with the statistics laboratory in Cambridge rather than computer science. There are various types of interactions that we have. I mean, we have joint projects. Some of us actually supervise or co-supervise PhD students, so we get to maintain an element of academic activity. We've given lecture courses, and there's a critical thing here which is sort of unorganized, and that is that we tend to go out together to the pub, we have a chat, we have lunch together, and this leads to informal collaboration, and it's actually in that area that it's very successful. Formal collaborations, when you wheel in legal and they start negotiating intellectual property and all these sorts of things, starts to get quite heavyweight. And of course, we don't actually want to have a legal agreement about what we can discuss in the pub. And the informal discussions are actually one of the things that's key here. And I'd say one of the things we have is nearly all our seminars are open. I looked at last month, and apart from Rick being there to give us a chat, and a discussion on the Com Plus garbage collector before it was announced, all of those other talks, the EXT at the end, says that it was available for external people to visit and come to the talks as well. When we started out, in fact, it was critical that we have people from the university attend our talks, because we were getting people in to do interview talks, and there was only 3 of us in the lab, which isn't much of an audience. So what we did was we drafted in huge numbers of people from the university, and researchers would come and they'd see this nice full audience, and they'd go, "This is a really go-get-it lab. Look how many people I have," and the vast majority of them were from the university. So indeed, most of our interview talks are open, although we don't advertise them as interview talks, unless the candidate really doesn't want it to be known that they're even talking or visiting Microsoft. We just leave it open. And of course, likewise, we attend a lot of the university seminars. The important thing here is, I know you're here in the University of Washington's, across the 520 bridge, which is not the best place. The thing here is that we are actually just a few minutes. It's like 2 minutes walk from our office to the computer laboratory. And this means that people will go, "Oh yeah, maybe I will just pop over to that seminar." If it was getting up to half an hour or 45 minutes, the level of interaction would just be lower. And it's one of the reasons that we continue to wish to be right next to the university departments that we cooperate with, because it makes that level of interaction much easier. So moving on to the areas that we cover, we have activities, and I'm just going to I'll give examples from some of these areas. Computer security, information retrieval, machine learning, networking, systems and performance, as I've just dubbed the group, and programming principles and tools. And I'll just give you some of the activities from these various areas. So I should point out that there's a crypto group here, and we're well aware of what they do. Security is concerned, crypto is one of the tools of security, of course. It's one of the things that you need to have in the toolbox. But of course, many problems in security, no matter how strong the crypto is, if, for example, your key generation sucks, then it's just not going to be secure. A number of the company's products in the past have managed to fall into that trap. So really concerned with, how shall I say, holistic issues in security, looking at the whole picture and trying to understand how key components like cryptography can actually be brought to bear. And one of the challenges, of course, in security is always dealing with the fact that as you increase the level of security, it increases the level of inconvenience to the users, and this causes users to just not use it or to do something foolish. The classic example of 2 bank managers who each had a key to the bank vault, but they shared a secretary, and so they would both give the secretary their keys to look after. A classic case of the user convenience completely circumventing the security that was supposed to be in place. So there is some work that's going on, working with the product groups now, looking at various of the products and what they're supposed to do, and we have so many security models and so many different ways of doing security in the products that some of these are actually fight against each other. One of the interesting things that's happening right now is the project that's called HTTP SIM, which is actually putting in a small HTTP server into the SIM of a cell phone. And the idea is this would become as the quote is, access enabling wallets on user controlled devices. A lot easier to describe what it is, but to basically put my keys and the information that gives me access to things inside this object, which I might have some trust in. I may not, for example, trust the random Windows workstation that I find in an internet cafe, because I have no idea how it's been configured or subverted. But maybe if I'm carrying around one thing, which is my trusted computing base, I might trust this. And when we get convergence between PDAs and cell phones, whoever manages to sort of win in that marketplace, I think one of the key things will be to work towards the user really having high confidence that this is a secure device. So it may be that we actually have to close the system down and prevent downloadable code into it. Anyway, this is a start. I was working on a small HTTP server to fit in with Windows for smart cards to actually start doing some of this, enabling access, putting security mechanisms into a cell phone. One of the other things that we have in this area is we work in computational number theory, really not so much on the theoretical end, but more on the practical end of implementing some of the algorithms, especially parallelizing the algorithms, to do some of these, attack some of these number theory problems. So, for example, we're involved in this GIMPS thing, the Great Internet Mersenne Prime Search. There we have what the Mersenne numbers are, and 1999 result from this group was that this huge number, which is over 2 million digits in it, is a prime. Now, why do we do that? Well, it is a classic because it's there. I mean, it's like, hey, isn't it interesting with just these prime numbers and look at these 2 million digits? But other areas, computation, applying large amounts of computation in the area of number theory has led to some interesting theoretical results as well. But practically, if we look at another group, there are about 20 people in this consortium, or 20 labs in this consortium. They've been working on the RSA challenge. RSA put out a challenge every so often and say, hey, try and crack this. And so last year, we worked on cracking RSA 155, which was the 155 decimal digit number that they put out and said, there, figure out what this is. Now, this is of more practical interest because, in fact, 512-bit keys protect various pieces of the global financial system. In particular, the Bank of England uses 512-bit keys in London. And as soon as this was announced, the Bank of England got on the phone and said, could someone come and explain to us why this is very, very dangerous? Because it had been stated that the ability to crack it would open up attacks on that infrastructure. I mean, the infrastructure, it's not on the internet. It is a closed network, but still, it could be open to an attack. And the only thing that reassured them at the moment is that the particular algorithms being used in these attacks, there's 2 stages to it. The first stage is very easily parallelizable. You can parallelize it with email. You can just send email out to people, and they do a bit of a computation and reply. And so you can get a very large number of systems working on the problem. The second phase involves linear algebra, which currently can only be done, the algorithms they have that attack it can only be done on a supercomputer. And that stage took 4 weeks of Cray time at CWI to actually do the linear algebra. Now, it's actually quite difficult for an organization to get hold of 4 weeks of Cray compute time without certain agencies of the US government finding out about it. So the thing that's reassuring is that at the moment, someone's going to find out that this attack is being mounted. But one of the things that we're actually trying to do is seek parallelization algorithms for that linear algebra phase, so that, for example, with a few thousand PCs, which is pretty easy for someone to put together, especially if you can convince them to do it with their screensaver, to seek to parallelize that stage and basically have a go at cracking the system. The key thing they need to do is just move to bigger keys, but a lot of this technology is actually in black boxes. It's not just, okay, let's release the new release of the software. It's black boxes that are doing this in the network, and they all need replacing fundamentally. So soon, in another year or two, we hope to get some results on parallelization of this, and by then, hopefully, someone will have actually increased the key size. So another area I mentioned, one of the groups is machine learning and perception, and I'm going to come back to machine learning in a minute. So I've sort of put down traditional machine learning here. The thing that whenever you say we're doing machine learning research, people say, oh yes, so that'll be your speech and your handwriting and vision systems and sort of traditional, let us say, artificial intelligence type problems. And so we do that. That's fine. I'm going to return later to discuss where we're trying to apply machine learning in a sense, more traditional computer science environments, but less traditional machine learning environments. One of the things that one of our researchers, Mike Tipping, has been working on is an algorithm, a technique which is in some ways similar to the support vector machine. He refers to it as the relevance vector machine. And the interesting feature of this algorithm, I mean, it's sort of state-of-the-art, so you might say, well, why do we use this rather than SVMs? And the key feature is that it's actually very compact in its online phase. So it runs pretty fast, and it has a small representation. So for example, if you want to do any of these problems, handwriting recognition or speech or all of these things, if you want to do them in a thing that has got limited computational resources, like your cell phone or your PDA, this algorithm wins simply because the online phase is faster and requires less memory. The computation you need to do before the training phase takes a lot longer. And they currently have an n-cube algorithm, and in a recent brainstorming session, they improved it to an n to the power 4 algorithm, so they could have backed off that. I mean, there are problems at the training phase because it's taking way too long, but the hope is, as with support vector machines, that bringing enough brain power to bear on that problem will come up with faster training algorithms. It's still viewed that it will take longer than the SVM, but perhaps for certain classes of device, we're happy to have a very long training phase if we can actually get the speed, accuracy, size, computational power required for the online phase decreased. So the example is handwriting in a PDA. So just to illustrate it, I mean, this is not my field, so at this point, if anyone starts getting serious about comparing SVMs with RVMs, I'll point you at the website. But I like the analogy, which is, support vector machines try to separate by sort of working out where the division is between the two types. So if we're just looking at a very simple example, trying to partition some data into two sets, support vectors will go through in the high dimensional space and try to partition it. And whereas relevance vectors will actually try to find characteristics of an area, and hence, rather than saying this is where the boundary is, try and say this is a prototypical type of this thing. And so the analogy is, rather than listing all the characteristics that are in between goats and horses, you basically say, no, you get a really goat-looking goat and a really horse-looking horse, and you say, that's a horse and that's a goat, instead of trying to sort of go through and look at things that are very similar and say, this is how I decided that was a horse and that was a goat. So it's interesting. There's an example, just a simple made-up example, where the support vector machine had 44 out of 200 vectors, and the relevance vector machine managed to get away with 3. But as I say, there's a penalty to pay in the training phase. So moving on to some of the work in vision, we had for a while, we had what the company refers to as a resident guest employee, which means that they were sitting in our office, they worked for our company, our subsidiary, which is Microsoft Research Limited, and but they were actually working for, in this case, the product group. It was, what was the product group? Photodraw, that's right. I can never remember. There's been so many photo products from the company. And this was actually something where it was quite good because, number one, he was a Frenchman. He wanted to live a bit nearer France than Redmond. And so we were able to support his personal desires. But also because of the relationship with the Vision Research Group, we were able to actually start introducing some things very rapidly to do technology transfer very rapidly. I mean, they were sitting there in the same building. So here's an example that I picked up. So if we want to do cut and paste, the sort of obvious thing you'd want to do, which is put an ear on this cuttlefish, then we might look at the current state of the art in the algorithms and pick live wire, which tries to work out, live, you're trying to figure out what the pixel contour is to extract this object. And it has a number of problems. You get leakage from the background if there was, say, the ear against the background. And when we cut and paste it across and attach it to the cuttlefish, we drag some of the background with it, and we'd like to minimize that. And you get some aliasing effects. So that's live wire. That's five-year-old algorithm. It's used. And so the thing that we've been working on is the algorithm that they've named Live Spline, which is now, rather than treat it as a series of pixels, to actually try and fit a curve to the contour, which is the edge of the object, and do sub-pixel edge detection, such that you're really, after all, the pixels are just some sampling of, say, some continuous object, and we really want to figure out what that object was in order to do the cut and paste. And also fix the computation which causes the background bleeding, so the alpha computation of how much background, how much foreground there is. So there's an example, just a made-up example of cutting a red circle from a yellow background. Live wire would traditionally get some yellow bleeding into the edge, and live spline doesn't. So the hope is that this research continues. There's various other features that they want to add to live spline, and the hope is that it goes into whatever PhotoDraw has turned into now that it's rolled into NetDocs, when we figure out what that is. One of the at the same time as Microsoft Research in Cambridge set up, coincidentally, Bill gave $20 million to the university to build a new computer laboratory. And the view was that we would move in and share space with the computer laboratory. That was a fine view when we were going to be 40, but now that we're already 65 with another 30 visitors at any time or 100 people, we were starting to look a bit large for the space that had been reserved for us in the building. So a decision was made about a year and a half ago to actually build our own building on the same site right next to the university computer laboratory. And here we see Roger Needham. This is one of the bit further back. You can't quite see, but PR had provided us with very attractive Microsoft Research hard hats. And at the front there is Alec Brewers. He's the Vice Chancellor of the University of Cambridge. And he's someone who actually was very keen, and he was key in getting Microsoft to come to Cambridge. He's ex-IBM. He's an engineer. He worked at IBM for 25 years. And his view is that Cambridge University really need to be attracting large companies to work together with the researchers. We're very good. Cambridge has been very good in the past at working with small companies. And there's like 1,200 high-technology companies just around Cambridge, small companies doing various things. But his view was that he wanted some large companies, and Microsoft was sort of the first one that he managed to snare in the computing area. And recently Marconi have announced that they'll be opening a research lab there as well. So the real estate people said to me, oh, could you put a webcam up so that we can see progress? There's real estate here in the US. They want to see progress of the building. And I said, well, okay, guys, but it is so cheesy putting up a webcam. I mean, it's like everyone's got a webcam. And a 2-year-old can go buy the stuff and set up a webcam. I said, I'll do it, but I'm not putting it on the internet and saying, look at this marvelous thing that we're doing. Here's a webcam. We were involved 8 years ago in putting the computer laboratory coffee pot on the web, and this was like, groundbreaking stuff at the time. But it's pretty tedious these days. So I started thinking about this, and I said, well, maybe we could do something interesting. I mean, we got these vision researchers, and they say they can reconstruct 3D models of stuff from a couple of pictures. So I said, okay, why don't we do this for the building, and then I'll put it on the web. So the idea is we want to try and construct a 3D virtual model of the building while we're constructing it. And we're going to set up cameras to do this. This is Cambridge from the air, and how am I going to do this? With the mouse. We are currently located right in the center of town, and this is fine. And we're going to move only a mile away to this large field, which currently is a construction site. This is fine. We will have nice new premises and everything else. There's only one downside to this, and that is that the pubs in Cambridge are there. And that line, there are no pubs to the west of that line, so we've got a long way to go to drink in the pubs with our friends. It turns out that Ian Leslie, the head of the computer department, is very concerned about this and the drop in social interactions, and is applying for a license for the computer laboratory so that we can serve alcoholic beverages. So this is what our building is destined to look like, something like this. We see the very important, down here at the right-hand side, this tent-like structure, very important in Cambridge that you have covered bicycle sheds, because we are having hundreds of car parking spaces in this building because as a commercial organization, planning allows us to do that. But it's going to be pretty empty. I mean, we did a survey, and actually out of the 200 parking spaces, I think we'll probably be using 15 to 20, because nearly everyone walks or cycles to work. Cambridge is a small place. If I go back, the center of Cambridge, as seen here, we're talking this is half a mile across. This whole site out here, the West Cambridge site, is being developed for science and technology. So computer laboratories moving out there. Physics is already there. Parts of engineering, disturbingly the Whittle lab where they fire up turbines. So it could be noisy out there. Well, what they did was they built a large concrete blockhouse to keep the noise in. The vet school, Schlumberger research, but eventually all engineering and science is moving out to this campus. Now this is huge. If you think about it, this is Cambridge University here and Cambridge City, and we're going to move out there. So this is a big plan. Now Cambridge University takes a long-term view. They bought this land 40 years ago. The residents on this street are complaining that, oh, there's building happening there. This has been a plan for 40 years, and the development is destined to last 25 to 30 years. Cambridge is it's sort of looking ahead, but it looks quite a long way ahead. It acquired this land and it has held on to it for that long, even though everyone's tried to grab it, because it needs the space to grow. So our plan, besides getting this building that we'll move into, and it'll be marvelous, and we'll have some big knees up, I'm sure, when we open it, is to put cameras on the Whittle laboratory, which is the lab just to the north, take pictures of the building as it goes up, and construct a 3D model, VRM model or something like that. Probably do little MPEG files, because that way people can download it if they don't have VRML viewers or if the performance just sucks. And build up this 3D model. So here we are. This is what it looks like on the 9th of August. I'm going to be radical and try and... there it is live. It's a pretty grey day in Cambridge. Sun's low in the sky. There's a couple of cameras up at the moment, and we're about to put up another 3, and then we'll start this activity. So at the moment, what we're doing is developing the theory and the software, and we can do this just with test images, and I've got an example here. Here's 3 images of the corner of a building and the reconstructions from the 3D model, and we see there are various artifacts, which of course we've got to work at getting rid of. Got a little video sequence here. This is a pretty low resolution image, which is what a lot of the jerkiness is. But the goal is to eventually build this up as a 3D model for our building, and in a sense advertise some of the research that we do in an easy to comprehend form to people. So we've got lots of work to do. I mean, there's lots of artifacts in that. We've got to match features better and what have you. So, hot off the press, and to the extent that I had to go and look at the source code 2 days ago to find out what they were actually doing here. And this is something that I know Rick knows about, because I went and pulled the files from his file space. Kentaro has been over visiting with us for several months now, and it's been a very fruitful collaboration. And somewhere along the way, in various discussions, the idea formed of taking various images at different focus settings, and then trying to build up the image which actually is completely in focus. So I've got a 3-second clip of video here, which will run through pictures taken, still image, but taken at different focal distances, and just going to last about 3 seconds, and it will move from focus in the far distance to very near. Oh, if I remember to click on it properly. Okay, so you see various of the pictures of the image coming into focus as you run through that, from the far distance coming through to the plant nearby, and even up in the top corner here, there's something that's very, very close to the camera lens. And you run through this sequence of images, do edge detection on the assumption that if there's a nice sharp edge, it's in focus, and then pick from whichever image has got the sharpest pixels. So you end up with this contour map showing the white where pixels have been chosen from very near, from a picture that had very close focus, to black where it's much further away. And you end up with this image. By selecting the pixels from the various images, you end up with a picture where there's focus all the way from, as I say, the top left-hand corner where there's a piece of material, I think. And is that a beer can? Bottle of wine, and all the way back to focusing at the far end. So I think this is it's sort of one of those. It's definitely one of those algorithms where when you know, it's easy to comprehend, and you sort of think, oh, it's one of those classic. Why wasn't this done before? But it's a really neat idea. So, you know, we might hope to enhance some of the company's plans in digital photography and cameras and products with this sort of facility. I mean, working out exactly how it's going to fit in, or how people are going to use it, or why they'll use it, is an interesting challenge, but it's certainly an interesting piece of research. So I said I would return to machine learning, and so I'm going to give you a few slides on, what shall I say, background on why we have arrived at, sort of philosophy of why we've arrived at where we've arrived on this. So I have a number of principles that I hold very dear, and this is that hardware fails, okay? It will always fail. It's the laws of physics, and you cannot change the laws of physics. Now, you know, this was identified as a philosophical problem as long ago as the 14th century, when Buridan's ass was going to find itself starving to death because it was incapable of choosing whether to go to this hay bale or this hay bale. And that's what we get. I mean, that's what you get at the level of a transistor making its decision about whether it's a 0 or a 1. Sometimes it might just sit in the middle and take an arbitrary long time to actually settle. So at this point, given that we've got this fundamental problem, we can try and engineer the probability down, but we can't get rid of it. I first came across this. I was never taught this. I actually had to spend time at a computer company trying to find a problem. And we racked our brains. We had two processors with a clock boundary between them going through a chip. And this chip, we applied all manner of logical reasoning to what it was doing. And it didn't help because the problem was an analog effect, and we were not going to get rid of it. And then we managed to engineer the problem down to basically a failure every couple of weeks. But it was starting to get extremely tedious to get it any further out than that. This is 15 years ago. And so what this means is that we've come a long way with logic and computer science and logical reasoning and everything else, but when we come to look at high reliability systems, we've got to start dealing with the fact that all our logical reasoning is not going to cause these physics problems to go away. We see randomness from other areas. I mean, people have worked very hard to try and understand networks logically in terms of, like, for example, quality of service. Can we provide quality of service? And people get confused and sort of say, we've got to make this a guarantee that we get 1 megabit per second. Well, in the real world, you can't guarantee that you'll do this. You can make statistical guarantees of what's the probability. And we would like to be able to engineer systems that reason about those probabilities rather than just say, oh, no idea. Either we deny the problem and say, we're not going to deal with probabilities in these systems, and we're going to say they're 100% reliable, or we accept that the problem exists, but we don't actually try and reason about it, and then we just get the customers complaining because they thought this system would actually stay up for 2 weeks, and it actually only stayed up for 2 days. And we get sources of randomness all over the place. For example, in networks, you just get, I mean, we could try to figure out and model why people do things, right? Why are they clicking on this web page? But we don't. We attack that problem statistically. We sort of say, well, let's try and model statistically a user, not try and reason about why they're clicking on a web page and things like that. So, you know, in networks, traditionally, we've used statistics because we don't know why someone picks up the phone. I mean, the phone network's a classic example. We don't understand the reasoning behind someone making a decision at this point in time to call their mom, right? So we attack the problem statistically. So we prepared, one of the things we do in Europe is we do a certain amount of public relations. You know, you may feel that the company has it rough in the US, what with the DOJ on the case and everything else, but the opinion of Microsoft in Europe is not as high as it even is in the US. I was trying to explain many of our areas of research deal with statistics, machine learning does, networking does, and as I'll show in a few moments, we're trying to apply it in other areas. I was trying to explain to journalists, and I had one of these, it may just have been me. I had sort of a road to Damascus experience. Something, you know, I went, that's why we do this. And I'd like to share this, and I don't know whether everyone else is going to say, that man's an idiot, I knew that already. But I thought I'd share it because it sort of changed my attitude toward why we do some things this way. So here's a well-known game. It is a board of 41 squares. There are a set of rules. We throw some dice. We execute the rules. Once you see the graphs of the moves, you might like to hazard a guess at what the game is. So one of the things we could do is just say, well, let's forget that we have rules and just learn by observation. Let's do machine learning on this game. Let us sit there and just look at what happens. And we watch some games and learn, and we can generate probabilities of being on a particular square. That's the average. And then we could do more. We could start looking at, given that I start from a square, where do I land? So there we see quite obviously a roll of 2 dice. We get a nice distribution associated with the dice, but there's something weird happening if we land on square 8. And somehow we sometimes get teleported off to square 40 and 41. Those are the rules executing. But we're not interested in rules. How far can we get by just learning what happens in this system? So this is the example I chose to try and explain why we sometimes go about learning. And I came up with 3 reasons that we might use learning technologies. Even though this example had rules, and we could have tried to write a program to execute the rules, maybe there are certain scenarios in which we don't know the rules, and that's when we would apply machine learning. Let's take the example, handwriting. For years, people tried to say, handwriting is an AI problem, let's sit down with Prolog and write those rules so that we can recognize handwriting. Didn't work. So we don't know the rules. Or we can't figure out the rules. There might be some rules there, but we just don't seem to be capable of getting there. But here's the one that I suddenly realized why I wanted to apply machine learning to systems. And that is, there are too many rules. So if we take the example of physics, you can sit down and you can start writing down equations of motions for every particle, and then you can try and reason about the behavior of a volume of gas. You don't do that. It takes way too long to model the behavior of all those particles. So what we do is we back off and say, what are we actually interested in here? In a volume of gas, say we're doing computational fluid dynamics, what we're interested in is pressures and temperatures and vortices and the way in which the bulk behavior of the system. In a network, a lot of the times, I'm not interested in this packet. I'm interested in, saying, quality of service. I'm interested in statistics about the whole stream of packets that form a video conference. So in physics, when we have all these rules that we can apply, and we can try and calculate from first principles the behavior of a gas, but we don't. We bring in statistical physics and statistical mechanics, and we reason about things statistically. And then we go and model it at that level, knowing that, yes, there are lots of rules that we could use individually, but it's computationally too intensive to do any reasoning about that. So here we go. We start thinking, machine learning has got this in its traditional AI problems of vision, speech, everything else. But today we have problems in systems, like, for example, in the internet, it is not possible to know the configurations of all the routers. Once upon a time it was possible. We've got a classic drawing of the ARPANET from circa 1964 or whatever, 4 machines on the network. You could know the total system, and you could reason about the total system logically, and then maybe sometime later you could roll in problems of failures. But if you look at the internet today, it's not just that the system is big, and hence you get some relativity problems, like it's difficult to know the actual state of the system at any given time because it takes time for that information to propagate. ISPs will not let their configurations out. It's commercially sensitive information. So if we want to start reasoning about the internet, we've actually got to accept that we cannot know the system and constantly trying to just reason about it logically. We can't do this because we don't know all the rules. So we can't execute a simulation of the whole network. So we do this today. I mean, a lot of the internet work looks at, well, what can we observe out of the system? We'd like to make it more principled, shall I say. So then let's look at system log files. I mean, you end up with a system, it's just crashed, and you go and pore over it, and you say, now, why did that happen? And actually, to try and build up a simulation of why a certain behavior happened, it could take way longer than actually just running the system and watching it crash. So you start looking at these things and saying, well, could we apply machine learning to these problems? Could we actually go in and start reasoning whether we have rules but we can't know the rules, or there are too many rules and we can't execute them, why don't we just try to learn by observation? So a particular axe that we've been grinding, there's a thing called explicit congestion notification that's being proposed for the internet. That is, packets go through the network, they go through a queue, there's some marking strategy which may mark a packet, and this is not a new idea. In fact, it's just it's the same guy putting it in as an RFC who did it for DECnet 10 years ago. It's called DECbit then. You mark data as it goes through. When it looks as though you don't wait until the queue's full. You know, at some point before that, you decide that I'll start saying I'm getting congested. Someone please slow down. The current internet works by waiting till the queue is full and then throwing the packets away, and relying on the end systems to react to the fact that packets got lost, the implication being there was congestion. Rather than do that, why don't we start marking explicit congestion notification using some strategy? The current RFC, that's the request for comments, uses an algorithm similar to what's called RED, for those who know about networking. It doesn't really matter what the algorithm is. At some point, you start marking packets because you want to get people to back off before you have to throw the packets away. Well, there was a proposal to actually look at an algorithm which was based on an economic model. It's actually using a derivatives analogy from economics to mark the packets. And this original idea was just to use 1-bit marks to say, you know, this packet experienced congestion or it didn't. And then you run some algorithm which tries to understand the state of the network and adapt its behavior. You know, you can actually take this all the way through and say, we'll actually charge for those packets. I mean, then you start getting yourself concerned about an infrastructure for billing. But we don't have to worry about that. We can just think about it in terms of this could still be an algorithm that's used in routers to mark packets. And it's a well-principled one in the sense that it's based on this economic model. In fact, our current work, we're using 8 bits because, and this is where we get some interesting tensions between the theoretical side and the actual implementation. You know, the guy implementing this said, I'm getting 1 bit per packet, and the time that it takes me to sort of gather together the bits to understand what the state of the network is, you know, that's many, many, many round trip times, and it's not effective. I really want to have a much better estimate rather than running for a long time to try and estimate what the state of the network is. Could we just please get a few more bits of information per packet? So the results I'll show in a minute use 8-bit marks, and they actually tell you whether to speed up or slow down. So you can actually tell someone slow down and slow down by this much from sort of some, you know, without any reasonable scale. It's a number between -128 and 127. You know, if you're getting 0 marks, basically, then everything's fine. If you're getting plus marks, the thing's going into congestion. If you're getting negative marks, you're being told to speed up. And we have an algorithm which is based on this economic model of willingness to pay. If you were willing to pay so many marks per second, and of course you've got to make sure in this economic model that you don't get mark inflation. I mean, you get all the economic problems with this. You don't get mark inflation. You've got to control the supply of the marks in the sense that people can't decide, no, I'm willing to send this many marks. So that's why if you actually take it all the way and say we're going to use real money for these marks, you're relying on the fact that people don't have an infinite supply of money. But you can use it just for marking as long as you control the supply and you say to people, you configure end systems, you're allowed to have this many marks per second. That's your budget. And the good thing is you can actually get proportional sharing of bandwidth now, and you can start doing what are called differentiated services within the internet at actually quite a fine grain. I mean, at the moment, people are trying to implement, say, a couple of classes of differentiated service so that you can get a better service if you pay more to your ISP. A lot of these use priority systems. Some of them use weighted fair queuing. But this particular technique, it gives us a very fine grain of being able to share out this bandwidth if we set the number of marks in the system appropriately. Now, the learning problem here is that when you look at what you're concerned about is all of the packet streams going through that queue. You're concerned about their aggregate behavior because it's their aggregate behavior that's going to cause the queue to overrun. And so we want to model the aggregate behavior and reason about that. One way of doing it is try to understand what every component is and then sum them and say that's the behavior of the system. Another way is just to say, well, I don't know what all those behaviors are. I mean, if you're in the core of the internet, you have got millions of different people going through your router at any given time. And you can't start reasoning about all that number of channels. And of course, you might get the situation where two streams, when they join together, they might be very bursty, but when you start adding them, you actually get a smoother traffic flow. Now, there's a big argument going on in the network modeling community at the moment about whether network traffic is fractal and whether it actually, you do get these smoothing effects. But the thing is that what we're interested in is we're sitting in a router, we're interested in knowing at what point should we start marking these packets to say that we're about to go into congestion. And it depends on what people are using the network for at that time. So in fact, in this example, the zero marks, the point at which we're going to say we're going to start marking, is something that we learn from the behavior of the system. So we move the zero mark level. We don't say when the buffer is half full, I'm going to start marking, because if the traffic is extremely bursty, that is not a good strategy. You want to mark much sooner. But if everything's really, really smooth, you can actually you can put off marking until you get to 90 or 95% full. The thing is that it's dependent on the traffic at the time. So it's a data dependency. And the thing to do there then is try to learn from the actual data that's flying through and use it as a predictor for behavior for the short term. So we learn from some number of seconds worth of traffic what we should be doing for the next few seconds. So this is why it comes into the thinking about learning algorithms at this point. So we have some crude mechanisms used in that simulator, and we're starting to look at others. We can look at it from a theoretical angle and use the statistics of large deviations, because, of course, we're interested in the rare events, so we're interested in looking at the long tails of these distributions. And we perform this measurement. And we've actually tried applying support vector machines to the problem of predicting what's happening in the network. There are no end of problems to do with stability and closed-loop effects. This is a control system, and there's always dangers. So this is an interesting. We'd like to know. We'd like to be able to reason about the stability of the system, even though we're learning from the data. So that's systems, and a couple of examples of some of the work that we're doing on the networking side. I'll now move on and just talk about the language group. The language group in Cambridge is certainly the largest, and we were very successful early on in recruiting, and it grew very rapidly. And this group, in a sense, is leading the way in its interactions with the product groups, having been the largest and longest established. They're really working well with the product groups. So the first thing that started was a belief that with the universal runtime, one of the goals we'd like to do is to be able to verify the code. Now, if you read the Java specification of what the verifier has to do, which is written in English, it keeps having holes found in it. So a couple of the guys decided that a useful thing to do would actually be to have a formal description of what the verifier should do. Now, this is not the same as verifying the verifier. This is simply saying, writing down in a computer language what the verifier should do, and the thing that it's actually used for is comparing the results of what that verifier does with what the product group are actually implementing in C++. The verifier that runs over the IL code that these chaps have written is written in ML. It's not the world's fastest verifier, so you don't want it running online. But it's useful for generating test cases and comparing. It's agreed that that specification, which is an executable specification, is what they're trying to do, as opposed to being written in English. And it gives a way of actually executing the specification to understand what its behavior should be. And this has generated coverage information and all sorts of interesting things, and that's much valued by the product group. I mean, at the time that this started, the researchers themselves sort of couldn't quite believe that they just get to go and keep writing in ML and it's going to be useful to the product group. It's not obvious that that was going to happen, but it's been very successful. And following on from that, and something that Anders was here just 2 weeks ago talking about, is the work on C# and generics, or templates, and it would be in C++, and polymorphism. And this has involved us in the high-level design work and generating the specifications, and we're actually doing the modifications to the C# compiler, let us say, to demonstrate how it might be implemented, and possibly say that that's what's going to ship in the product. But the goal is to add this design for generics into version 2 of the .NET platform. It nearly made version 1, but there were just some timing issues with when they believed they could deliver and do all the testing in the product space. So, and it's something that, it's interesting. Anders gave there's an interesting quote I found, actually. He gave an interview that appeared on this website, and there was a follow-up discussion at which the following was said: I hope they talk to someone who's heard of ML and Haskell. Now, this is music to Simon Peyton-Jones's ears when someone says Haskell, because, we employed him in spite of his strange fetish for this Haskell language. And we're never going to get him off now, because now he's got Haskell, can generate intermediate language, and he's got the .NET platform doing lots of stuff for him. The thing is that I think we brought to bear on this problem, a good set of theoretical understanding of languages and a wide range of different language implementations to actually get a really good design for this generic stuff. And it was good to hear Anders referring to it as amazingly great stuff in his talk. One of the things that started here, which was Project 7, to get many academic languages targeting IL, it's something that this group has done a lot of support for and worked with, because they've done ML and they're doing Haskell.
Can you go back a few slides?
Sure.
One more. Thanks. So I just wanted to understand something a little more. The validator and the verifier, you said, had been transferred, are being used by the product group. Can you say a little more about how they're actually using it? You said test case generation. So, you said it had been very successful, so I just wanted you to qualify that a little bit more.
There was an English language specification, and there was a body of C++ code. And people would look at some intermediate language and say, I don't think this should get through this C++ verifier. The thing that they now have is they take it and they put it into the ML verifier, because it's the executable specification, and everyone's agreed this is the true specification. And it says, yes, it should pass, or no, it shouldn't. And at that point, you go back to your C++ and decide whether you need to fix it.
So they've actually integrated it into their testing process?
It is part of the testing process. And they generate test cases. Like the things that sort of exercise all the nooks and crannies of the verifier have been generated and checked with this, and then they go into test cases. So it's generated a lot of test cases.
Thanks.
So a final one that I would give, and we're still trying to figure out what Microsoft as a company could possibly do with this piece of technology, and we've tried all manner of places to sell this. When Simon Peyton-Jones joined us, he had a collaboration already running, which was working with a financial company in London, which did options pricing. And this led on. This was supposed to be something to do with software engineering, in the sense that it was supposed to do with the process that they used to generate their financial software. And of course, Simon was still trying to convince everyone that Haskell is the one true way, and all their financial software should be written in Haskell. And there are many good reasons why it should be. However, what we got is recently is a chap called Jean-Marc, who works for Société Générale, and Simon and Julian, and we had on the one side someone who's been doing all this financial engineering and working in the financial industry for a long time, and then we get together with people who do programming language, and you get into this thing where the financial guys are talking about all sorts of weird stuff like Bermudans and Americans and Europeans. I mean, maybe some of you know the difference between an American and a European option. I now know because Simon's explained it to me, and the point is he's done it using a language. And on the other side, we had the language guys now going functions types, lazy evaluation, Haskell, Haskell, Haskell. So, in trying to explain to Simon what the financial side of it was, and to Julian, they realized that actually there was a language that could be generated to actually express a financial contract. And here's an example. I mean, I'll tell you at the end where lots of these talks can be found. I mean, it's one of the most riveting talks I've heard in a long time, actually. And as I say, we're still trying to figure out what we do with this. So you actually can end up with a language that you start with some fundamental, simple contracts. I'm going to give you $100 on a certain date. And you can start joining them together. For example, here is the classic golden handcuff contract written in this language. There are 3 dates, there's a number, and there's a price. And in return for that price at some time T3, I will receive some MS shares that were based on a price at the time, at T3. There's a timeout on this. The thing truncates at some point in the future. There's a timeout of 7 years. And it's not valid until it's run for a year or 18 months or whatever your option is. But at any time, you can decide to either exercise that option or throw it away. I mean, you can actually say, I don't want to take that option and give 0 value. The thing about this is that I was reminded that when it was halfway through the talk, I was reminded of a number of PhD theses I've seen in my time, where people generate this huge edifice of theory and language and mathematical equations, and you're going, right, but what are you going to do with it? Having generated these combinators for how to take contracts and build complex contracts, pursuing the goals of good language design. I mean, what we have here is a domain-specific language. We want economy, we want expressiveness, and efficiency. It turns out that having described this contract, you can start reasoning about valuing contracts. Now, at this point, you have to inject economics, okay? And that's not where we have done any research. But there are well-known, trusted, used formula in the economics world for valuing contracts. And what this does, it gives a way of taking a contract which is now specified and applying those rules. And the key thing is the evaluation engine. When you take a contract and a model of the world, exchange rates, currency rates, interest rates, you do all of this, you apply that, and that's where the financial skill comes in, the modeling of economics. At that point, when you apply it to this language, you find out that the valuation of these contracts composes. So given that you've joined two contracts together using one of his combinators, the valuing engine does it as well. Now, it turns out that this is exactly what these people had been doing in these companies, except they'd been doing it by hand in C++. They had been writing, and whenever they had a new contract, so the traders would go out and they would do outrageous things. They would come back and say, I've just invented a new contract. It's like a Bermudan, but I've added this bell and whistle on the side. And the computer guys would be told, okay, you have to now write the code that will value this contract for us using our valuation engine and the rules that we've decided to use and our predictions of the future. And this would take months of effort and C++, never mind just the writing of the code. It was error prone. So, and also they would find situations where the dealers would lie to the computer system. They would go in and say, it is a Bermudan. Comment, this isn't really a Bermudan, it's just a bit like it. And the financial industry has difficulty with these weird contracts because they sort of, 10 years down the line, this contract's still live, and so-and-so has gone, they've retired, they've moved to another company, and people are going, what on earth was he on about here? So what this has given is a way to actually formally specify financial contracts. It's still a long way to go, but the financial industry is really excited about this. So at this point you say, what on earth does Microsoft do with this? I mean, we actually don't deliver this software into that space. I mean, it's not, you don't sell 10 to the 8 copies of this stuff. But it's extremely interesting, and we're sort of trying to figure out what our relationship is with this. There's now a small startup that's actually going to go and do this in France and write a compiler for it and everything. So if you ever get the opportunity, never mind that Simon Peyton-Jones is a highly amusing speaker. It's well worth having a look through it if you haven't already seen it. So finally, I'll just give you a few pointers. I mean, we do have some stuff on MSR Web, as everyone else does, of people and groups and stuff. The other thing that we do is every Friday we have one of us or an intern or someone gives a talk to the whole lab. And so I've actually extracted quite a few of these slides from those Friday talks. And those are mostly, they're nearly all available as PowerPoint online. So to finish up, I'll just, I mentioned Simon, and he's been quite productive in the last couple of years since he's joined us. It's very good to see. I did receive a piece of email, though, that had come from a program chair recently, where some people are concerned that Simon's starting to monopolize the language conferences, and he's appearing everywhere. And they're talking about referring to the DOJ for a possible split up into Peyton and Jones. So on that note, feel free to fire any questions at me. Thanks for listening. Silence. Great. Thank you very much.